before made, right? Because then it's almost the end of the term already. Okay, the equation we'll talk about now is, different books have different terms for it. I think the text that you have, Zill calls it the Cauchy-Euler equation. Sometimes other books you'll see it's just called the Euler equation. Some books even call it the equidimensional equation. I'll give you the reason for that in a second. Now, this equation is a differential equation with variable coefficients, but it's a very special form. What you'll see is that when we write the equation, we'll have coefficients on the left that are powers of x, but the power of x will match the derivative. So here's the general form of the equation, and this technique that I'm going to show you works for any order. So it's called the Cauchy-Euler equation. Okay, so the left-hand side is the usual linear business that we had, right? We have something like, right? an, that's going to be x to the n, nth through y with respect to x, right? Before, sometimes we had constant coefficients, we wrote it as an nth derivative, right? In the general theory, we put an of x, okay? What happens now is, you see is you can have constants over here, and then the power of x will match the order of the derivative. So then we have another constant, a sub n minus 1, let's say, x to the n minus 1, n minus first derivative of y with respect to x. And then we keep going down, dot, dot, dot. Finally, a1x dy dx plus a0 times y equals, let's do the homogeneous case first, okay? Equals 0. We know how to do non-homogeneous once we solve the homogeneous, but this is something new. We've never seen an equation like that. Okay, where a sub I equals a constant. This is for all the guys, right? Y equals 0, 1, down to n. Okay? So everybody see what's going on over here? Okay, it's a linear differential equation, okay? And what happens is that when you go to this term, there's some number x dy dx. The guy in front of that is x squared second derivative. So the power of the independent variable is matching the order of the derivative. Now, of course, many equations aren't in that form, but could be put into that form, right? Suppose I just want to take this, I divide through by x cubed, okay? Okay, it's still going to be an equidimensional, but sometimes you have to, fool around with it a little bit, to see it. But let's just assume basically that's in this form where we explicitly see the power of x matching the order of the derivative. Okay. Now you may say, okay, nice, you can show me how to solve this, but really, is this of any practical use? And the answer is yes. Okay. Usually I'll do this in undergraduate, but one of the first courses you take in graduate school is theory of plates and shells. Okay. These are like, what's a plate, for example, a manhole cover, or even a diaphragm that's on, a speaker. Okay. There are many things that can be modeled as plates. Okay. And there's a treatise that's very famous, put out by ASME, and the first or second chapter deals with circular plates. Yeah, a manhole cover would be like that, right? And there's certain boundary conditions over there. And the problem that's posed in that book and others is to find the deflection of that thing under a certain type of loading. A car goes over it or something, or you step on it, obviously it's going to be deformed to some extent, right? And the theory of plates is developed, like I said, in many books. And what happens is that whole chapter of circular plates, all the equations governing the plate deflection are an Euler equation. So it's something that, and again, if you took this, in the math department, they would just do it and you'd ask them why and they'd probably throw up their hands. But, okay, if you look back historically, this was done in the context of people, engineers who were looking at vibration, also just deflections of plates under loading, okay? The equation, it's nice that it comes out like that. Hence, that was the motivation to say, can I actually solve these things analytically as opposed to just doing a numerical solution? Okay. Now, I'm going to do this a little differently than the book and allow us to basically cover every case like in less than 3 minutes. I'll show you what it is. Okay? Here's a claim, and then we'll verify it. To change a variable, and change independent variable. To change of a variable, what is it? I'm going to go from x to t, let's say. X equals e to the t transforms the equation, that one, right, two constant coefficients. Amazing. Okay? So one choice you have, okay, but I'll show you an easy way to do it, is you have an equation like that where the power of x matches the order of the derivative every term. Make the transformation of independent variable, right? Because remember, y is the dependent, x is the independent. X equals e to the t. What will happen is you get a differential equation involving y, dy, dt, and you'll see it's constant coefficients. You know how to solve constant coefficient equations, right? So you do everything with y as a function of t, the way we did it before, and now you just, at the end, you just transform back. Whenever you see t, you have to put log x, right? Because x is e to t, t is log x. Okay. Let me show you, at least, in the first few derivatives, why this works out, okay? Well, it's the chain rule, right? Okay? So if I go with the equation, a0y stays a0y. There's no independent variable there. But I have to look at x dy dx. And I'm claiming, basically, if we transform variables, x equals e to the t, x dy dx will involve just dy dt with a constant. Let's do the chain rule on that. Okay, what's dy dx? We all know it's the derivative of y with respect to t times the derivative of t with respect to x, right? But dt dx is just a reciprocal of dx dt, and dx dt is e to the t, so that becomes e to the minus t dy dt. Okay, that's what would happen over there. So the dy dx becomes e to the minus t dy dt. They say, whoa, wait a minute, you made it worse. Before it was x dy dx, now it's e to the minus t dy dt. But that's not what I need, right? The equation has the term x times dy dx. So what happens to x dy dx now? If I multiply both sides through by x, x is e to the t, the e to the t cancels, and I find that it's dy dt. So at least on the first derivative, it's done it, right? So instead of having now a number x dy dx, we have the same constant a1, dy dt, constant coefficient. At least on the first guy, okay? Let's do the second one, and you'll see in general how it works out. I just got to use the chain rule again, that's all. And I'm not going to do any more derivatives on the second, because it shows, you'll see exactly how this thing, you'll see the sequence. The second y with respect to t, okay, second y with respect to x, sorry. The second derivative of y with respect to x, that's d by dx of dy dx, right? Okay? And therefore, the second y, okay, I don't want to use primes because you'll get confused. The second derivative of y with respect to x equals the derivative with respect to x. Let's work out what we did dy dx. It e to the minus t dy dt, right? I just stole that from over there. Okay. Now here I got a function of t. Here I got x. I'm going to use the chain rule on this. Okay? And that's going to be the derivative with respect to t of e to the minus t dy dt times what? dt dx, which again is just e to the minus t. Okay? Let's see what this gives us. I'll pull out e to the minus t over here. Let's use the product rule. E to the minus t, second derivative of y with respect to t, right? Minus e to the minus t dy dt. Okay? And if we clean this up a little, we find that the second derivative of y with respect to x, pull out e to the minus t, now you get e to the minus 2t, and what do you have over here? You've got the second derivative of y with respect to time, or respect to t, whatever that may be, minus dy dt. Okay? And again, I remind you, what's in the differential equation? It's not the second y with respect to x. It's that times x squared times a constant. So what happens to x squared second y with respect to x? I multiply on the right by x squared, but my substitution says x squared is either 2t. And you see how this guy knocks out, and you just get the second derivative of y with respect to t minus dy dt. And the same thing happens for the third, fourth, and higher derivatives. Okay? So this transformation takes our Cauchy-Euler equation and transforms it into what? A constant coefficient. Now that's one way you can proceed, but there's an easier way, okay? And I'm just going to summarize like I did the last time. Let's look at all the possibilities, okay? See, the person who has transformed variables, and he has constant coefficients, right? What does he do? Remember, it's now y versus t is a constant coefficient. Remember what we do? We look for a solution of what? E to the rt. When we're doing y and x, it was e to the rx. You have to be careful now. The constant coefficient case is y is dependent, t is the independent. For a constant coefficient equation, you assume a solution e to the rt, right? But e to the rt is just x to a power, okay? So what you can do is, rather than make a transformation of variables, just assume a solution to the Cauchy-Euler of the form x to a power, okay? And then that's the same as the guy who does it in the t domain as e to the rt, okay? And then we have to go over all the cases now, of course. What happens if you have single roots, multiple roots, and complex? All I'm going to do, though, is I'm going to leverage off, I don't know why the book doesn't do this, I'm just going to leverage off what we did on the constant coefficient equation, right? So what happens in practice, actually, is that you don't have to transform to constant coefficients, but knowing that this transformation of variables does accomplish that task, you can write down all the solutions depending upon what the values of the roots of the characteristic equation are. So, case one. So this is, again, for Cauchy-Euler equations. Be careful now. Okay. Case one. So, sorry, let me just over here. So, how do we start? We take the, and we're going to do plenty of problems, after we get all this on the board. Assume a solution y equals x to a power. Let's say x to the r. Okay, why are we doing x to the r? Because the guy who has constant coefficients, he's going to assume a solution e to the rt. So therefore, I can just assume a solution x to the r. What happens, as you'll see, when you plug in x to the r over here, you'll find that you get a polynomial in r with constant coefficients. And you get roots, R1, R2, whatever, okay? So, case one now, distinct roots. The solution to the homogeneous equation, before I see that again, would be C1, x to the R1, plus C sub 2, x to the R2, plus C sub n, x to the R sub n. Okay, C1, C2 down to C sub n are arbitrary constants. And we have x to the first root, x to the second root, down to x to those. And these are linearly independent because we're assuming that the roots are distinct. Okay, now we have to do the case of like a double root, okay? And then even case two, multiple root. And I'm going to do exactly, this will parallel the notes that you have on the constant coefficient multiple roots. Again, you assume a solution x to the r, but now maybe r equals 3 comes out twice, okay? How do you get that missing solution? Okay, so the independent solutions, okay, I'm going to talk here, not write everything down. When I put this little brace over here, I'm basically just going to list the independent solutions corresponding to the multiple root, okay? Multiple root, okay? So say r equals r1 is a root of multiplicity k. Multiplicity k. Okay, so for example, you had a double root, k would be 2. But maybe, r equals 2 is a triple root. I'll just do the general case because it'll cover everything. Suppose r1 is a root of multiplicity k. Then the linearly independent solutions are going to be what? Well, remember, you assume the solution x to the r, so certainly x to the r1 will work, right? No question. Now, go back to the guy who transformed to constant coefficients. Okay, he's basically y versus t, right? And suppose r1 was a multiple root. He'd do e to the r1t, right, which is rx to the r1. And then what does he do next? He does t e to the r1t, remember? And what's t? Log x. then you get x to the r1 times the log of x. See? Back when we had constant coefficients, we take that exponential solution, e to the r1t, we multiply by powers of t. But now powers of t become powers of log x. Okay? And then the third, if suppose it was root of multiplicity 3, he'd then do what? He'd have x to the r1, right? And then he'd have a t squared there, but that would mean log of x squared. And obviously, all the way down to x to the r1, log of x to the multiplicity take away 1. If you count those up, those are going to be exactly k linearly independent solutions corresponding to the multiple root r1. Okay? And then the third case is complex roots. Okay? Case 3. Complex roots. I'll just do one complex root here. What to do, right? Complex root. Okay? What are the fundamental solutions over there? Okay, complex root, say r equals alpha plus or minus I beta. And remember, complex roots always occur in conjugate pairs, right? So you have 2 plus 3i, you always get 2 minus 3i. Okay, go back again. Imagine you transform variables by x equals e to t out of constant coefficient equation. What were the solutions for a complex root when we had constant coefficients? E to the alpha t cos beta t, e to the alpha t sine beta t, right? Well, what's the e to the alpha t? That's x to the alpha. Cosine of beta t. Unfortunately, that becomes a log x. Kind of weird, a cosine of a log, right? And then the second independent solution would be what? For the guy who had constant coefficients, he'd have e to the alpha t sine beta t. Well, that means x to the alpha sine of beta t, which is now log x. Okay? So those would be the two solutions. So you see, you just leverage off what you did. Knowing basically that this transformation gives you constant coefficients, we know how to solve constant coefficients for all 3 cases, and just a matter of remembering what the guy would get in terms of y and t, and then transforming it right into x, if you want to. Now, of course, if you wanted to, you don't want to keep this all in your head.